So, Ian, if you'll help me with which evens, where did we start?
10. We did 10 and 12,
Okay,
and then 14 to 38 every other even. And that's on page 158.
gotcha. So, number 10 is 4t sine of pi minus 4t plus cosine of pi minus 4t. Number 12 is 3 pi over 2 times cosine of 3 pi t over 2 minus 7 pi over 4 times sine of 7 pi t over 4. Then 14 is cosecant x over cosecant x plus cotangent x. 18 is 2 secant of x times the square root of secant x plus tangent x. 22 is negative 4 times parentheses 1 plus cosine 2x, close parentheses, times sine of 2x. 26 is 2 secant cubed of 2 theta plus 2 secant 2 theta times tangent squared of 2 theta. Number 30 is 2 cosecant squared x cotangent x. 34 is 1, and 38 is negative 8. That was all the ones on that page?
Yes.
And then on section 4.2, I think I have these circled. So
12 to 42 every other even.
12 to 42 every other even. I don't have that circled at all. All right, so number 12 is x plus 2, negative x minus 2 over y plus 3. And the slope at the point in question is 3/4. Number 16, dy dx is 3 minus 2x minus 4y over 4x plus 8y. And it's defined everywhere except for where y equals negative 1/2 x. Number 20 for part A, the equation of the tangent line is y equals negative x minus 1, and I'm assuming part B was it a normal line?
Yes.
Is y equals x plus 3. 24 for part A, it's y equals 2x. And for part B, it's y equals negative 1/2 x plus 5 pi over 8. 28, dy dx is negative y to the 1/3 over x to the 1/3. D squared y dx squared is 1 over x to the 4/3 y to the 1/3. Interesting. Oh, I know why they did that. Okay. 32 is negative 3/5 x to the negative 8/5. 36 is negative 4 times 1 minus 6x raised to the negative 1/3 power. 40 is x to the negative 3/2 times the quantity 2x to the negative 1/2 plus 1 raised to the negative 4/3 power. Did you do 44?
No.
So is that it? Okay. All right. Happily answer any questions you have about any of those. Brett?
16.
16 on, sorry, the first page or the second page? Second page? Okay. I think this is the first page. Go.
The homework is says,
Color me
It
surprised.
is every other even.
it says page 176, 2 to 42, every other even.
No, that's 167.
Yeah, I mean 167. Is that means from 2 and then 26 and then 10?
Yes?
Oh yeah, okay.
You were reading the 2, 8, 12, and 16, which is the
For the first half of the homework, I did every single even.
Okay.
That's
Oh,
my fault.
then I might have done the wrong questions.
Did we all do that?
I was like, they weren't the ones that I had circled.
Wait.
Yeah, I did 12 to 42 every other even instead of 2 to 42 every other even.
Oh, because
So I did all the wrong questions.
Okay, well, let me
I-
give you the answers to the other ones. Hang on a second.
I did 2 to 26 every single even, and then I did every other even.
I think we missed the 70.
All right,
75.
So it was the ones I had circled. Okay, so 2 is 6y minus x squared all over y squared minus 6x. 6 is secant y. 10 dy dx is negative x over y, and the slope is 0. 12, oh, then we're good.
14.
Yeah.
So then the next one would be 14, not 12. Gotcha. So negative 1 over sine of y, it's defined at every point except where y is an integer multiple of pi. Number 18, a, y equals 3/4 x minus 6 1/4, and b is y is negative 4/3 x. 22, y equals 2 for part A, and for part B, x equals the square root of 3. 26a, y equals pi, and b, x equals 0. 30 dy dx is 1 over y plus 1, and d squared y dx squared is negative 1 over y plus 1 quantity cubed. 34 is 1/4 of x to the negative 3/4. 38 is the quantity x squared plus 1 raised to the negative 3/2 power. 42 is 5/4 of sine to the 1/4 of x plus 5 times cosine of x plus 5. Better?
Yeah.
Yep.
All right, so Brett, you were asking about which one?
Just so it's the ones that were actually on my homework. I'll ask about 22 because I had the same problem. I was
22? Okay.
I was dividing out dy dx completely.
Okay.
Don't know why.
Let's take a look. So what are we supposed to be doing on 22? Find the tangent lines and normal lines? Okay. All right. So when we start taking the derivative, we're going to have 2x minus the square root of 3. Did you leave this negative square root of 3 out in front? Or how did you handle the fact that it was negative square root of 3 xy? Because there's a couple of different ways you can do that.
Okay, now I don't know if it's right. I put in parentheses x times dy dx plus 1.
Oh, after this?
Yeah.
Yeah, that's fine.
Okay.
So that would be x times dy dx plus y times 1, right? You don't have to write the times 1, but yes. Equals 0?
Yeah.
Oh, wait a minute. Hang on.
No, plus 4y times dy dx.
Yeah. Plus 4y dy dx equals 0. Okay, that looks good. Then what did you do?
I distributed the square root of 3.
Okay, let me suggest it would be easier, and I'll do it your way, but it'd be easier to go ahead and substitute in the values at this point. Okay, but we can go ahead and do it your way. So this would be 2x minus the square root of 3 times x times dy dx minus the square root of 3 times y plus 4y dy dx equals 0. Then what?
Then I got confused because I felt like I was dividing on dy dx, but I'm really not.
Yeah, what you want to do is put all the things with dy dx on one side and everything else on the other side. So I would write it like this: 4y plus the square root of 3, excuse me, minus the square root of 3x are both being multiplied times dy dx, right? Equals, move everything else to the other side, so that'll be the square root of 3y minus 2x. And then divide by 4y minus the square root of 3 times x. Okay?
Is it negative sign in front of square root 3?
Here? Which, I mean, there's several square roots of 3 here.
I mean, the answer is it like the negative?
Yeah, that's a minus square root of 3x.
I mean, the upward.
This one,
Yeah, there's negative r.
it'll be positive because I moved it to the other side of the equation.
I got it wrong.
My bad.
Okay. What other questions do you guys have? And Brett, if you want to ask one that's not on the homework, that's fine.
Can I add 74 on the first page?
On the first page? Sure. Which of the following is an equation of the tangent line to the curve? Oh, I was like, wait a minute. So it gives you the parametric equations. So we know that dy dt is going to be cosine of t, and that dx dt is 1 plus sine of t. So then dy dx is going to be cosine of t over 1 plus sine of t. Okay.
I didn't put 1 plus sine t. That's
What did you have? Did you have 1 minus sine t?
no, I don't know what I did. I had cosine of t under sine of t, just like that.
You had cosine of t under sine of t?
Oh, okay, no, I see what I did. So when I took the derivative of t minus cosine of t,
Yep.
I just canceled out the t entirely instead of realizing there was 1 t.
Gotcha. Yeah, it's real easy to miss that. You have to be careful. Any others you have questions about? Yes, sir.
38.
On-
4.2.
On 4.2, okay. You said 48 or 38?
38.
38, okay. We're supposed to be finding the derivative and the second derivative. Oh boy.
Big question.
So there's a couple of different ways you can do this. So my question is, how did you rewrite the original function?
Y equal to x divided by, no, x over x squared plus 1 parentheses outside, so 1.
Okay. So you just rewrote this as to the 1/2 power?
Yeah.
Okay. So then do you use the quotient rule?
Yeah. I probably should make it makes it 1/2 into negative 1 side.
Then you'd have to use the product rule.
Also, I see.
So yeah, either way, I don't think there's a huge difference. So here this is going to be the denominator, which is x squared plus 1 to the 1/2, times the derivative of the numerator, which is 1, minus the numerator, which is x, times the derivative of the denominator, which is 1/2. And this is where most people make their mistake, x squared plus 1 to the negative 1/2 times 2x. Did you remember the 2x?
Yeah.
Good.
Hey, yes, sir.
Over the denominator squared, which will just be x squared plus 1.
Oh, I don't know what I was thinking. I changed it to the x squared plus 1 parenthesis of the 3 over 2.
3/2,
Yeah.
but you're squaring 1/2, something to the 1/2 power, so it'll be to the first power.
Oh, yeah,
And there's a fair bit of simplifying that still needs to go on here. So this is x squared plus 1 to the 1/2 power minus x squared times x squared plus 1 to the negative 1/2 power over x squared plus 1. Oh, I know why. Because you were looking in your crazy solution manual. No, I'm not kidding. You got to stop looking at that thing all the time. Don't look at it partway through the problem.
yeah.
Make yourself do the problem. So now what I'm going to do to get rid of this negative exponent, which makes this a complex fraction, is I'm going to multiply by x squared plus 1 to the 1/2 power on top and bottom. So that's going to give me x squared plus 1, because to the 1/2 power times something to the 1/2 power is that to the first power, minus x squared over x squared plus 1. This is to the first power times this to the 1/2 power is this to the 3/2 power. And this, which was pretty ugly a moment ago, is now really simple.
Nice.
And then we can find the second derivative just using the chain rule. It's negative 3/2 of x squared plus 1 to the negative 5/2 times 2x. The 2's happily cancel. And that's negative 3x over x squared plus 1 to the 5/2 power.
That's way better.
Just staring off into nothingness. Any other questions? Okay. Then let's go on to derivatives of inverse functions. This is actually a pretty small topic in terms of what's on the AP exam. It doesn't even show up every single year. But it's easy enough to where if you know how to do this, it makes some problems really easy. If you don't know how to do it, then you just miss that problem. I mean, it's almost impossible to kind of figure it out on your own. So Remember that for inverse functions, f and g are inverses of each other if and only if f of g of x is equal to g of f of x is equal to f, or equal to x. Y'all did that in pre-cal? Or did you do it in Algebra 2?
I don't remember. I haven't learned.
I don't remember.
I,
But that looks familiar to you at least?
Yeah.
That two functions are inverses of each other if you take the composition and you just get whatever you put in?
Yeah. I
Okay.
think we did that in Algebra 2.
how
I don't think we did that. I don't think we did that in pre-cal.
Okay, so it's been a while.
Yeah.
But that's the definition of of two functions that are inverses of each other. Sort of like taking half of x and multiplying it times 2. 1/2 x and 2x are inverses of each other. Right? All right. So when this is true, we can say f inverse of x is equal to g of x, and g inverse of x is equal to f of x. They are inverses of one another. It doesn't matter which direction you go. So, how does this involve derivatives? Well, for any point a comma f of a on the graph of f, there will be a point with coordinates f of a. Notice that's the same coordinates but just reversed on the graph of g. So if the original graph had the point 1, 3, its inverse will have the point 3, 1 on it. It's guaranteed. Okay, this has the effect of making the graph of f and the graph of g reflections of each other over the line y equals x. So it might look something like this. By the way, this is something that looks a little bit like a logarithmic function, and this is a little bit like an exponential function, which are inverses of one another. And if you have the point a f of a on this, you have the point f of a on this one. Notice that since the y and the x are reversed, that means that the slopes of these would be reversed. They would be reciprocals of each other, because normally it's the change in y over the change in x. The other one we could do the change in x, the original x over the change in the original y to get its slope. So, if f and g are inverses of each other, we know that g of f of x is equal to x. And you could have started the other way around. It doesn't matter which one you start with. If I take the derivative on the left side and on the right side, on the left side I get g prime of f of x times f prime of x is equal to 1. That's just using the chain rule on the left side. Dividing both sides by dividing both sides by f prime of x, I get that g prime of f of x equals 1 over f prime of x. Or, if you prefer, at a particular point, g prime of f of a is equal to 1 over f prime at a. So that means if I go back to this, if I was to draw in the tangent lines, the slope of that line would be f prime at a. The slope over here at this line is 1 over f prime at a. Those two slopes are reciprocals. And this is also g prime at f of a. The derivative of g at the x value f of a. This is the derivative rule for inverse functions. Now, we use this occasionally to help us find derivatives of things that are weird, but are inverses of one another. But more frequently, we'll do it to find derivatives of things where it's really difficult to find an exact inverse for something. I'll show you what I mean by that in some of these examples. So let's move on. And we're going to skip that verify that the derivative of f of x is the square root of x. I find that it doesn't really help students. I used to do that, and then last year or so I've been like, that doesn't really help anybody understand this, so we're not going to do it. All right. So let's let f of x be equal to 4x cubed minus 2x plus 1, and f inverse denote the inverse of f of x. Find f inverse's derivative at 3. All right. So first, let me point out that if you were to, don't worry about writing this down, but if you were to write y equals 4x cubed minus 2x plus 1, again, going back to algebra 2, usually what you did to find the inverse function is you switched the variables and solved for y, right?
Yeah.
That sounds familiar?
Yes.
Good luck solving that for y.
Yeah.
It turns out to not even be a function, and I don't have a clue. I don't think you can. I don't think you can write that as y equals some function of x. Okay, well, So if I want the derivative of the inverse function at 3, well, remember that this on my inverse function was the output of the original function. So the first thing I'm going to do is go, okay, 3 is equal to 4x cubed minus 2x plus 1. That's pretty difficult to try and solve unless you just kind of think about it and go, oh, hey, look, what x value makes that true that's really simple? 1. Right? Everybody's good with that? So what we're going to do is we're going to take f prime of x, which will be 12x squared minus 2, and then f inverse prime at 3 is going to be equal to 1 over f prime at 1. That's the derivative rule for inverse functions. The input for these is never the same number. Well, I shouldn't say never, but practically never the same number. So that's going to be just 1 over 12 times 1 squared minus 2. It's 1/10. So I can actually find the slope of the tangent line of the inverse function without ever finding the inverse function. That's pretty slick. All right. More often on the AP exam, they'll write it in this sort of format. Let f be the function defined by f of x equals x cubed minus x. If g of x is equal to f inverse of x, and g of 0 equals 1, find g prime at 0. All right. So I want g prime at 0. Well, g and f are inverse functions of one another, right? So g prime at 0 should be equal to 1 over f prime of g of 0. Now you're like, wait a minute, that's not the way we wrote it before. Okay. If you want it written the way we wrote it before, it'd be f prime at g of 0 is equal to 1 over g prime at 0. That's the derivative rule for inverse functions, but if you think back to some basic arithmetic, you can switch those two, right? And it's still equivalent. So g prime at 0 is going to be equal to, let's go ahead and find f prime at x. This is 3x squared minus 1. F prime at g of 0. Well, what is g of 0? 1. It tells you that. So that's 2. This is a half. These can be pretty easy problems, but it's easy to get all kind of tangled up and wait, which one am I doing and all that kind of stuff. You just have to remember that it doesn't matter which one you're starting with because they're inverses of each other. Here's another example. I think there was one like this on an AP exam several years ago. And part of the reason I can't say specifically is that they haven't released the multiple choice section from the operational exam, which is the one that most people take, in ages. It's been, I don't know, 20 years or something since they've released one of those. They usually release the international exam or one of the other exams, not the year that it's, not like the fall after it's given in the spring, but the fall after that or something. And they don't always even release those. A lot of times with those, like I have access to last year's, so May of this year, I think it's the international exam, but it's kept secure. We're not allowed to show it to students, blah, blah, blah. We're not allowed to post it, all these other kind of things. So anyway, I haven't seen, the upshot of that is I haven't seen all the multiple choice questions on the operational exam in a long time. So let's take a look at this one. Let g be a differentiable function such that g of 2 equals 4, g of 4 equals 3, g prime of 2 equals 1/3, and g prime of 4 equals 5. If h of x is g inverse of x, and h is differentiable, find h prime at 4. And now you can really, really, really get messed up. Okay? I sort of prefer, because you're kind of used to this order, I sort of prefer to go, okay, I'm going to put 1 over h prime at 4. Then this is going to be g prime of h of 4. And you may be going, well, how am I supposed to figure out what h of 4 is? They don't tell me any of the h values. Well, remember that if g of something is equal to 4, then h of 4 is that something. So it's not this one that we need, it is this one that we need. If g of 2 equals 4, by the definition of inverses, then h of 4 is equal to 2. Remember that with inverses, the input and the output are switched. So this is going to be g prime at 2. G prime at 2 is 1/3. So that means that H prime of 4 is equal to 3.
Complicated.
It feels a little odd at first. Once you get everything kind of straight in your head, but it's easy to get tripped up on this. And I still sometimes have to think about it. Okay? For the most part, though, I find that doing it this way is helpful to me. You know, when they just say find H prime at 4, I put that over here because that looks more like my formula, which said that F prime of G of A is equal to 1 over G prime of A. And I try not to get too caught up in the F's and the G's. It's just two functions that are inverses of each other. Because I could have just as easily have written that G prime of F of A is 1 over F prime at A. So I find that if I start with this part that I'm looking for, I do a lot better. Okay? And, well, that's it. Nice short lesson.